So in this video, we're talking about section 2.1, 2.2, and 2.3. So we're essentially discussing linear functions and how to think about linear functions, how to find slope, how to find intercept, how to work with different forms of the line, and then how to find a solution of a system of equations through algebraic and graphing means. Okay, so first off, functions describing quantities that have a constant rate of change are linear functions. This is where we have some input such that a 1 unit increase in that input creates some predictable level of change in the output variable. So we get a 1 unit increase in the independent variable, has some effect on the dependent variable, and that some effect is just the slope. That's what we mean by this functional form. So f of t is equal to b plus m times t for some constants b and m. Well, b here, this is just our intercept. This is where the line crosses the vertical axis, and this m, this is capturing the contribution of a 1 unit increase or a 1 unit change in t, right? How do we know that t is our independent variable? Well, look, this is a function of t. So our dependent variable is a function of the independent variable t. Okay, so b and m are the parameters for the family of functions. B is the functional value when the input is 0, right? So if t is 0, then this drops out and we just have f of t is equal to b. That's just the intercept. That's natural, right? If the independent variable is 0, if our x is 0, then we just get our whatever is the y value, whatever is the intercept. And m represents the constant rate of change. That's important. It's a constant rate of change. That's why before I said we have a linear function when there's some predictable effect of an independent variable and the dependent variable. Predictable in the sense that it's constant. It's the same effect. Whether we have, irrespective of where we are on the function space, right? So whether we're going a 1 unit increase from 0 to 1 or a 1 unit increase from 1,000 to 1,001, we expect the same rate of change in a dependent variable if we have a linear function. Okay. In terms of other definitions, we say a function is increasing if its output increases as the input increases. So if we increase x, if the y increases as well, we say the function is increasing. And you can think what this means. We have a function that's rising, right? It's rising from left to right. It's rising up. It's like an arrow pointing to the northeast. We say a function is decreasing if its output decreases as the input increases. So this would be an arrow pointing to the southeast. So now we have an arrow that's starting in the northwest and going down to the southeast. So it's a downward sloping line. And then slope-intercept of the form of the line is just our y equals mx plus b form, right? F of t is equal to b plus mt. This is called slope-intercept form because we have our intercept and we have our slope. And once again, b of f of 0 is the initial value. This is the vertical intercept of the graph. That's when we evaluate this function for a value for t at a value of 0, then our independent variable is 0, and the dependent variable takes on a value equal to the intercept. M is the rate of change. It gives us our slope. If m is positive, the function is increasing. The graph is rising from left to right. If m is negative, the function is decreasing, and the graph falls from left to right. Then lots of times we're going to think about the units of measurement, particularly when we're doing analysis problems. So given some q is equal to b plus mt, the units of b are the same as the units of q, since b is the initial value, right? So whatever are the units of the dependent variable, b has to have the same units, because when the independent variable takes on a value of 0 and this mt term goes to 0, drops out, q is equal to b, they have to have the same units. Now the units of m are going to be the units of q divided by the units of t, since m is the rate of change of q with respect to t. M has to tell us how q is changing with respect to t. So it's got the units of q divided by the units of t, and I'll say a little bit more about that in a little bit. Okay, so here's an example. So stop the video and do this. Give me the slope with units. Interpret the slope of this expression, or of this equation. Q is equal to 156 minus 13p. Where this gives us the number of widgets sold as a function of price. Okay, so finding intercept and slope. The slope, well, our equation is already in slope-intercept form, y equals mx plus b form. So the slope is just minus 13. We get that for free. right? This is like our x, this is like our y. And then to get the units, what do? Well, it's going to have the units of the dependent variable q divided by the units of the independent variable p, right? So the units of our y are widgets, right? Q is in widgets, it's a quantity of widgets, and then x is in dollars, right? The units of x are dollars, right? Because price is measured in dollars. So the slope has to be widgets per dollar. So we have minus 13 widgets per dollar, which tells us with a 1 unit or a $1 increase in price, we get a 13 widget per dollar. We get a decrease in the total amount purchased of 13 widgets. That's because here our y is q and our x is p. If you think back to here, where we say the units of m are the units of q divided by the units of t, since m is the rate of change of q with respect to t. Right? And then here's just a really quick comment. In economics, we usually think of p as being our dependent variable and q as the independent variable when we draw graphs of the supply and demand curve. But that's an interpretation you don't need to worry about until if and when you take that class. All right, so we can interpret our slope. I said this a little bit a second ago, but basically we begin our interpretation with the denominator. That's our input. That's our input variable, and then we make a statement about the numerator. That's our output variable. So we say m equals minus 13 says for each $1 increase in the price of a widget, there's a 13 widget decrease in the quantity sold. And that's standard for a linear equation. Basically what we say is for a 1 unit increase in the independent variable, we get an effect. The effect on the dependent variable is just whatever is the slope. And then it adopts whatever is the sign, right? In this case it's negative, so a 1 unit increase in $1 increase means a 13 widget decrease in consumption, or the amount that's sold. Okay, so now we can interpret the intercepts. So state the vertical intercept with units and interpret. State the horizontal intercept with units, then interpret. What's the vertical intercept? Well, we get that for free. It's just this 156. And that's got to be in widgets because it's a quantity. Quantity is equal to 156 widgets when p is equal to 0. How do we find intercepts? Well, if I want to find the q-intercept, I have to set p equals to 0. So I plug in p here, or plug in 0 for p. If I want to find the p-intercept, I set q equal to 0. So I plug in 0 for q. If I do that, you can see what we're going to get. If q is 0, we'll have 13p is equal to 156, or p is equal to 156 divided by 13, or 12. And that's got to be in dollars, because it's giving us our p's, right? P prices are measured in dollars. What's the interpretation of the vertical intercept? Well, this is the number of people. Q equals 156 is the number of people who will buy the good, or who will accept the good if the price is free. And what about p is equal to 12, the horizontal intercept? What's that interpretation? Well, that's just telling us that that's the price at which no one will buy widgets. So we can, speaking like an economist, we can say if the horizontal intercept here, if p is equal to 12 is the horizontal intercept, that's the at that point we say nobody in this market values widgets more than $12. No one in the market likes. Everybody in the market likes their $12 more than they like the widget. Okay, so here's how we can do this with a series of steps. Consider the equation. Step 1, we draw our set of axes with q on the vertical, p on the horizontal. Step 2, we plug in p is equal to 0 to show that q is equal to 156 widgets when p is 0. So we say at a price of 0, we can sell 156 widgets. And this really just summarizes everything I said on the previous slide, but here spell it out for you. Okay, so then on the next one, we plug in q is equal to 0 to find our p-intercept. So we find p is equal to $12. And the interpretation, at a price of $12, no widgets will be sold. Everybody likes $12 better than they like widgets, or nobody likes a widget more than $12. And here's the picture. Right. Oh, and what's this dot doing here? Absolutely nothing. It has no interpretation whatsoever, so you can't forget that exists. What's this one? This is our vertical intercept. This is when the price is 0. We get a quantity of 156. This is our horizontal intercept. This is when, at a price of 12, none are sold. And here's the equation of this line. Q is equal to 156 minus 13p. Okay, so next thing we can do is we can think about finding the equation of a line. Suppose we have 2 points, 0, 4, and minus 2, 1. How are we going to find the equation of this line? Well, what we do is we can use our slope formula, which is just rise over run, our change in the y's divided by a change in the x's, y2 minus y1, x2 minus x1, and we can find the slope. And all that's important here is that whatever one we designate as point 2, that we use the y coefficient or y coordinate from this point here and the x coordinate from this one here. So we have y2 minus y1, x2 minus x1. It doesn't matter which point is point 1 and which point is point 2, just as long as we're consistent applying this formula when we make our substitution. And we find the slope is 1.5 or 3/2. We already have the intercept because 0, 4 gives us the coordinates for the vertical intercept on the line going through these 2 points. So we know the equation is y is equal to 3/2 x plus 4. Well, what am I doing down here? The check step, well, I used this point and this slope to build our line. Let's check the other point to make sure that this point lies on that line. So I'm going to evaluate this equation for x is equal to minus 2. If I do that, I need to fix this right here. This should be a minus 2, shouldn't it? This needs to be a minus 2 because I'll get a minus 2 and then the 2's will cancel and I'll get minus 3. So this right here, correct this sort of mentally. I'm drawing a 2 here. That's supposed to be 2. And then sure enough, when we evaluate, we get x is equal to minus 2. We get y is equal to 1. So indeed, this point is on that line. Okay, so we can also express functions in point slope form. If we do this, if we know the slope of a line at some point on the line other than the vertical intercept, what do? We use point slope form. So here's one way to represent point slope form. It's just f of x, or you could think of f of x as just y. Y is equal to y naught plus m times the quantity x minus x naught, or y equals, that's exactly what I said. The graph passes through the point x naught, y naught. The slope or the rate of change is m, and that's just the interpretation here. That's why we call this point slope form. Sometimes the equation for the linear function in point slope form is written like this. I actually prefer this. You could see very clearly when you stare at this that this is essentially the slope formula, right? If we divide this through both sides by the quantity x minus x naught, then you'll have y minus y naught over x minus x naught equals m, right? If we divide this through by this quantity, then we have our slope formula. That's exactly where the point slope formula comes from. So, all right, so here's an example. Why don't you stop the video and do these examples. Look and see, given this function, given this rate of change, can we find the linear equation using that point slope formula? And then given 2 points, can you do this? Okay, so f of 3 is equal to minus 4. This tells me that my x is my input, so my x is 3, and my y is my minus 4. So here's my point. X naught, y naught is just 3 minus 4. Has a slope of minus 5 because that was my rate of change. I can just evaluate using this formula, right? So I can plug in my f of x is just going to be, this will stay the same. My y naught is going to be my minus 4. My m is my minus 5. X is going to stay the same, and then my x naught is my 3. And just distributing right here, I have minus 5 times x is going to give me minus 5x. I have minus 5 times minus 3, that gives me a positive 15. And then adding, I have f of x is equal to 11 minus 5x. And then we're done. Okay, in this other one, we have 2 points. We have 4, 12, and we have 6, 30. Whichever is our input, that's our x. So my 4 is my x, my 12 is my y, my 6 is my x, my 30 is my y. What's my slope? 30 minus 12 over 6 minus 4 is 18. Alternatively, suppose I would have switched this around and have 12 minus 30 over 4 minus 6. I think that's what I did in class. Then you'd have minus 18 over minus 2, still 9. Right? So it doesn't matter which one is point 1 and point 2. What matters is that you have, you keep the points together. So these 2 points, this y and this x come from this point. This y and this x comes from this point. That's what's important. Okay, so now we can use point slope form with this particular point. So I'm just going to replace in my equation, I'm going to replace the values. So I have g of x is equal to 12, that's from my y naught, plus 9, that's my m, times x minus x naught. X naught was 4. And I distribute my 9, I get 9x, and I get minus 36. I collect like terms, or I just perform this addition, and I get minus 24 plus 9x. And then what am I doing down here? Well, let's test using the other point. So let's use this point 630 to make sure it's on this line. This will help me know if I've made a mistake. So I'm going to evaluate g of x, which I found right here, by plugging in 6 for x. When I do this, I get minus 24 plus 54, and that's positive 30, which indeed is the y that's associated with this x. So I've confirmed that this point lies on this line. So that's good. Okay, a couple comments. We're often interested in knowing which input values to a linear function give a particular output value, and that question gives rise to a linear equation. Linear equations also arise when we want to know what input leads to the same output from two linear functions, f of t and g of t. If we graph those functions, f and g, on the same set of axes, then the value t, where the functions are equal, corresponds to where the graphs intersect. And then we'll do an example, and I'll show a picture. Just a quick comment, most linear equations have a single solution. If you have a system of equations, you typically have a single solution. You could also have no solution or infinitely many solutions. What happens when we have no solution? This is where the lines are parallel. What happens if we have infinitely many solutions? That's where we deem that the lines are just multiples of each other. It's just the same line. So that would be like the line x, x plus, let's see, the line y equals x plus 1, and the line 2y equals 2x plus 2, right? So you factor out or divide by 2, you find out, oh, it's the exact same line. That'd be a situation where you'd have infinitely many solutions because it's the same line. Okay, so here's an example. Consider the market for lemonade in the neighborhood. The quantity of lemonade is given by Q is equal to 14 minus 4p. This is the amount of lemonade that people would like to purchase. Suppose the quantity of lemonade supplied by the neighborhood kids is given by this quantity, Q is equal to 4 plus 4p. So this is the amount of lemonade that the kids are willing to sell. So then what's the price? For what price are kids willing to supply the same quantity of lemonade as potential buyers are willing to purchase, and how many lemonades are traded? So pause, think about this, and then come up with your answer. Here's our graph, right? You could just plot these functions. You've got a graphing calculator, so you can always draw these graphs and find where they cross. That's going to be our solution. If you do this, you find, oh, look, it's at a price of 125 and 9 are sold. I think this is probably kind of a generous price for lemonade, and maybe a generous quantity given that price. But anyhow, that's the solution to our equation here. All right. And then algebraically, well, to solve this, I can say we want to have the same quantity, want to have the same price. Let me just replace, let's substitute for Q. Rather than having Q is equal to 14 minus 4p and Q is equal to 4 plus 4p, let me replace these Q's with one of these expressions. So I have 14 minus 4p is equal to 4 plus 4p, because these are both equal to Q, so that's a legal substitution. And then just solving, 10 is equal to 8p, or 10 over 8 is equal to p, or 125 is equal to p. So this tells me the price that makes potential buyers willing to purchase the same number of glasses of lemonade is the same as the same number of glasses that the kids are willing to supply is a price of 125. Right, so at a price of 125, kids are willing to sell as many glasses of lemonade as people are willing to buy. And I can check this quantity. I can evaluate one of these things, or both, ideally both, for the price of 125. And if you do that, you should check both, do that, check both, and confirm that you'll get a quantity of 9. Okay, very good. Let me know if you have any questions.